Hi and welcome back to R for BRFSS. I'm Jennifer, your instructor for this tutorial series. We are now in the second video of our two-part segment on chi-sqaured test. So we just cleaned our data and now we're going to analyze it. So let's pick up where we left off in R. Our data file has been cleaned and it looks good. So let's pull our code back up. What we need to do before we start analyzing our data is set our survey design, which we've done previously when we were working with the weighting variables. So the first function we're using is called svydesign. This is from the survey package. We set our ID to tilde1, our strata to tilde x underscore ststr, our weights to tilde x underscore llcpwt, and our data is the cg17 underscore chi-sqaured. And we will call this new data file, or rather this weighted survey design, cg17 underscore chi-sqaured underscore dsgn. So this is our survey design from the survey package. We also want to set a survey design from the survey R package because that package allows us to do that package is more compatible with tidyverse syntax. So we're getting pretty good at coding using tidyverse functions. So when we use the survey R package, it just makes us easier to kind of integrate the coding that we're already familiar with. So that function is called as underscore survey underscore design. We start with the argument dot data equals cg17 underscore chi-sqaured. Our ID is, in quotations, x underscore psu. The strata is x underscore ststr, and the weights again are the llcpwt, and these are in quote marks. So let's go ahead and run that. We'll run both survey designs at the same time. So just copy and paste it over. Let's take a glimpse at both. So cg17 underscore chi-sqaured underscore dsgn. This is the survey design from the survey package. And yep, it's a data frame. We have all of our observations, and the one variable just refers to the fact that it's a survey design. So now let's glimpse the survey design from the survey R package, which is cg17 underscore chi-sqaured underscore design. And I mean, we see the same thing, right? It's still a data frame. We still have all of our observations, and the variable is the same. So yeah, we just set two survey designs. One is more compatible with tidyverse. So we'll kind of go back and forth between both. And actually, running chi-sqaured tests in R is pretty easy. I described this in our last segment on logistic regression analysis, but you kind of have three options for looking at crosstabs, your chi-sqaured test value, and then looking at them together. So the first is survey table. Let's, for example, choose the disability variable, so that dis, as our first variable of interest, and the second variable of interest is the limit join. So this is our function. Tilde dis plus limit join, and our data file is the cg17 underscore chi-sqaured underscore dsgn. And I said this is our function. I meant this is our formula. Okay, so this is our formula for the survey table commands. So let's take a look at that. And now we see this is the weighted number of people with no disability and who don't have joint pain, the weighted number of people who don't have disability and do have joint pain, the weighted number of people who do have disability but don't have joint pain, the weighted number of people who do have disability and do have joint pain. So this is our weighted tabulation across those two variables. Now to get our chi-sqaured test statistic, we have the same arguments in the parentheses, but the function instead is survey chi-sqaured. So let's go ahead and run that as well. All right, so our test statistic, our F statistic is 551.38 degrees of freedom, and our p-value is less than 2.2 to the negative 16. So it's statistically significant. And here I should also clarify that within this argument, you can set the test statistic. So let's look at survey chi-squared. Let's look at that function. So now it's opening the internet. And our statistic, we can change the statistic. The default is the F statistic, but we can change it to a different, let me find out where it is. Yeah, so the default is the F statistic, but we could change it to chi-squared. We could change it to, I'm not seeing all of the options. Oh yeah, we can also change it to walled, adjusted walled. So you can change your test statistic to, I guess, anything that you would like related to chi-squared test, but we're just keeping it as a default where statistic equals F. All right, but you can change that test statistic if you would like. Okay, so if you want to look at the survey table and the survey chi-squared together in one line of code, kind of as a package deal, what you do is you wrap the survey table function in this summary wrapper. And we have the same arguments inside of the parentheses. So let's just copy and paste that over. And now we have our crosstabs and our chi-squared test results. So if that's what you want to do, that's great. Let's hop over to our article and look at what we're actually supposed to be calculating though. So that's here. All right, so in their table, if you're only interested in the chi-squared test for independence and statistical significance, all you have to do is run that command summary parentheses survey table parentheses then your arguments. And you get this whole last column. But they also included these other columns, which should look familiar if you watch the segment on prevalence estimates. So we will also recreate these columns on prevalence estimates because they're slightly different than what we previously did. So before we just looked at prevalence estimates across male and female respondents, but here we're going to differentiate between disability and non-disability groups in addition to the total sample. So we're going to try to replicate every column in this table. So to do that, this should look familiar as well. This is our code from the prevalence estimate section. So we start with our survey design. Then we put a pipe, group by. First, we want to just look at one variable. So we'll use the joint pain variable as an example. We'll then include another pipe, summarize for the proportion of the survey mean. That will give us the proportion, and we also want to include the standard error, and we'll filter out just where the respondent answered affirmatively that they do have joint pain. So to run that line of code, our output is, we have our variable is the joint pain variable. So 9.98% of people across the population reported joint pain, and the standard error on that is 0.004. So in the table, in the article, that would be these first two lines. All right, but we also want to look at the next four columns for people with and without disability. So to code for that, in the group by function, we also specify not only joint pain, but also that disability variable. So this is more or less the same code, except for in group by, we include dis, the dis variable. So let's run that again. And now we see people without disability. 35.4% of people without disability do have joint pain. The standard error on that is 0.0220. 64.6 people with disability do have joint pain, and that's the standard error on that. All right, so if you want to work outside of R and just set up a table in either Excel or Word, now you know how to calculate all of the numbers that you need to complete that table. But I like to be more efficient and don't really like copying and pasting things over. So what we're going to do instead is try to recreate that table in R by like binding the columns together and then binding the rows across all of the different variables. And I just saw that my computer is dying, so just give me a second to plug this in. All right. Okay, so in order to create that table, what we want to do is, so this is the line of, these two lines are the commands we just ran. So looking at joint pain across the whole population, then looking at joint pain by disability group. So we're going to set those two commands to the objects called pop for population and by dis for by disability group. So pop only looks at limit join. By dis looks at limit join and dis. Okay, so let's run those lines of code again as they're set to their object names. So now we have pop and by dis ready for us to use. Now we're going to create another object called dis group. So we start with by dis and we filter out where disability equals 1. So we have that. So this is our disability group. Now we want our no dis group for our not disability group. We start with by dis and filter out where dis equals 0. All right, and so we can just check on that. If we look at dis group, we see we only have that line where disability is 1. If we look at the no dis group, we only have the line where disability equals 0. And what we want to do is bind those three objects which we've created. So we have our population, our dis group, and our no dis group. So we'll call that P1. And we're calling that P1 because that's part 1 of our table. Because in the article, they have kind of two parts on the table. The first part is prevalence estimates. The second part is chi-sqaured. So we're calling this P1, where we want to column bind pop, dis group, and no dis group. So let's run that. And if we look at P1, we'll see we have all of our values are in place, and this looks great. But when we further go on to run this across all of our variables and then bind our rows together, so we recreate the table line by line, these limit join columns will cause problems for us because each variable will have columns in that place with that variable name. And then when we try to bind the rows together, it won't match up those columns because they're called different things. So what we want to do is drop columns 1, 2, 3, 4, 5, 6, hold on, 1, 2. We want to drop the columns that are called limit join. So to do that, let's reset P1, where we take the P1 object and we keep all of the rows, but we take out, so we do this minus. Minus means to include all of the columns except those contained in these parentheses, which are columns 1, 4, and 8. So let's run that line of code as well. And if we look at P1 again, now we see we still have our numbers, which is what we want, our proportions and standard errors for the population, disability group, and non-disability group, but we don't have these limit join columns. So in doing this, this will allow us to bind our rows later after we work across all of the variables. So that's part 1 of the first row in our table. For the chi-sqaured test, what we want to do is set our use this chi-sqaured function, and we'll set this chi-sqaured function to the object called A, which is just a random arbitrary object name A. And when we look at A, you see we do get our chi-sqaured results. But this is kind of weird, right? This is not a tibble, which when we're working with the other function, this looking at the prevalence estimates, the output is a tibble. So we can kind of treat it like a data frame where we can pull out columns and rows. But the survey chi-squared test results don't give us a tibble. It gives us this kind of like, I don't really know what it is, but it's not possible to pull out values from this result. So what we have to do is we have to unlist A. And that breaks it down into its pieces, kind of line by line. All right, so that's good, but we still can't really pull values from this. What we have to do now is set A as a data frame. So actually, I should reset the object A to that unlist, and then we're going to create a new object called B, where we set this unlisted unlisted object A to a data frame. And in doing that, let's take a look at B. Now we see that this is a data frame where we have two columns. The first column is, actually we really only have one column. This column on the left is the name of these values on the right. All right? So what we are interested in is the F test statistic and the P value. So from this data table B, we want rows 1 and 4. So we're going to pull out row 1 from B. We'll call that F stat for F test statistic. And then in order to work with it further down the line, we also have to set it as a data frame, because that will allow us to bind the columns and then later bind those rows as well. So we have two lines for F stat. For the p-value, we want the 4th row from the B data table, and we also want to set that as a data frame. So let's run these 4 lines of code together. Just run them. And now we want to bind the F stat and the p-value together, which we'll set to an object called P2 for part 2 of the table. All right, and then when we look at P2, we see that we have our F test statistic and our p-value. And even though in the article they just put an asterisk to indicate statistical significance, I'm just going ahead and attaching the full p-value anyway. Okay, so now we have part 1 and part 2 of our table. So let me change this to part 2. So to get the first row of our table, we want to column bind part 1 and part 2. And now we have the first row. This is exactly what they have in their table. Proportion of the population, standard error, proportion for the disability group, and standard error, proportion for the non-disability group, and standard error, their chi-squared test for independence, which we're using the F test statistic, and their p-value. So now we have the first row. So what we want to do is, let's just review how many lines of code that took us. So that took us this many lines of code. I don't know how many that is, maybe 20, I don't know. It took us this many lines of code to create the first row of our table. And we have to do that across 8 secondary condition health variables, plus we are also interested in the respondent sex. So we have male and female, so that's 2. So we have to do this 10 times total, so 9 more times. And as you know, if I have the chance to write a function to write less code, then I'm going to do that. So I tried to write a function. Let me show you what that looks like. Oops, this is getting kind of small. I guess you can't really see that. All right, so what I did is I basically copied and pasted everything that was on the previous page, except where we had our health variable, I put y in its place. And if you recall from the prevalence estimates tutorials, there is an issue when you're writing a function and you're using tidyverse syntax, because the tidyverse doesn't require quotation marks around the variable names, but other packages in R do. So R gets confused about quotations. So to resolve that kind of confusion about quotations, you set your variable argument, or for in our case y, we write the function nquo parentheses y, and that kind of, I don't know how it does it, but that basically resolves quotation problems. And so anywhere that you would have just put plain Y, instead you put exclamation point, so 2 exclamation points Y, which is pronounced as bang bang Y. All right, so this should resolve our quotation issues. This is the first part of our table, P1, and then we also use the survey chi-squared function, so we need the bang bang Y again in here. And this is the second part of our function, and we bind those part 1 and part 2 together. That should give us that should produce 1 row. And I've called this function CST for chi-squared table. All right, and then this is this function argument bracket. That is the function for writing a user-defined function. Right, so we name the function, we call the function command, we put our stuff inside of these brackets, bracket here, a bracket there, and that is our function for 1 row on our chi-squared table. So I'm just going to go ahead and run that in R, copy and paste it all over. And let's test it out on one of our variables. So CST, chi-squared table, is the name of our function. LMTJOIN3. So that's that's the health variable we just looked at before we wrote the function. And the problem is, so we get an error message that in our data frame, our design variable is an undefined column. And so I thought that this issue would be resolved by using enquo, and then bang bang Y, because that worked for us when we did the prevalence estimates. So I was thinking, maybe the issue is not with this section on prevalence estimates, this part 1, but maybe the issue comes in with the part 2. So I broke up the code a couple of times. This is, I rewrote the code, but I ended it at P1. So I'm calling this function now CST_1 for, my first try testing out the chi-squared table function, only looking at the prevalence estimate part. So this is the function. Let's paste it in. And then when I do CST_1 on LMT join 3, oh well, I spelled that wrong. LMT join 3, it works. Okay, so it's not the first part of our function that isn't working. So our enquo and bang bang Y resolution was correct. So the next question is, maybe it's part 2. All right, so I did CST_2 for chi-squared table, my second try on the code, where I included everything. I specified again that we want Y to be enquo parenthesis Y. I put bang bang Y anywhere we want our variable to be called out, and the rest is the same. All right. So let's run that function, and let's test it out again on that same variable. So chi-squared table _2, the variable is LMTJOIN3, and it still, it couldn't find our column. So there's a problem here in the second part of our function. So I thought, so it's looking for the column bang bang Y. It's looking for that Y variable. So I tried a third function where I only looked at the survey chi-squared function. Again, I put the enquo bang bang Y, and I ran that function again. So let's just all at once for CST_3, and it still can't find it. Okay, so here I was so frustrated because enquo should work, and in fact, I searched for enquo on the R documentation, and I tried out so many different variations. Like I tried expra and expra. I tried a lot of things, and I couldn't resolve it. So that made me really irritated. But I didn't give up hope yet, because I thought, well, this single line of code didn't work in our function. But maybe this other stuff that we did after we ran the survey chi-squared commands, this other stuff that we did to unlist it, set it as a data frame, and select our columns, and then bind those together, maybe that will work. So I wrote that function, cst_4, and it worked. Well, it will work, but what you have to do instead is with this function, we specify the argument a. So whereas before, when we were calling our previous functions, in this spot we had y, we called the variable name. Here, that argument a is actually the survey chi-squared function. So we have a function within a function. So our cst_4 is a function that we wrote. The survey chi-squared tilde dis plus limit join comma our survey design. That is a function that we had previously run towards the beginning of this video. So when our argument is the survey chi-squared function, it works. So now we have part 1 and part 2 of our first row on our table that we have written functions for. All right, so what should have been just a really easy one function, we should be able to get that first line of code with just this cst function. But what we have to do instead, for whatever reason, is we have to kind of approach it from two sides. So we need to run the cst1 function on our variable, then run the cst4 function on our survey chi-squared argument, rather the survey chi-squared function, and then bind the cst1 and the cst4. So part 1 and part 2. All right, so let me just walk you through these 3 lines of code, and then I did that over all the variables, so we'll just copy and paste them in. So R1 P1 is row 1 part 1. This is cst_1. This is our chi-squared test _1 function that we wrote, which we want to, our argument is the limit join variable. And then R1 P2 is row 1 part 2. This is our cst_4 function, where our argument is a survey chi-squared function. And then we want to set the object R1, where we bind together our results from row 1 part 1 and row 1 part 2. All right, are you with me? Okay, so let's copy and paste that in. And when we look at R1, we get what we're looking for. Okay, so it was kind of roundabout. I really wanted to just write one function to get this single line of code, but we ended up having to write 3 lines of code, which is much more efficient than the 20 lines which we previously wrote. But you know, it's not perfect, but I think it's an improvement on what we had before. So let's review. In R1, we have our proportion for the population and the standard error, proportion for the disability group and the standard error, proportion for the non-disability group and the standard error, the f-test statistic, and the p-value. So I ran those functions over all of our remaining health variables and the male and female variables. So let me just go ahead and copy and paste all of those in. And we don't see any error messages. So then what we want to do is bind all of those rows together. And we should end up with a table, which we have. Okay, so we have a table. This is great. This is we're almost done, actually. So this is the proportion of the population, standard error, proportion of the disability group, standard error, proportion of the non-disability group, standard error, f-test statistic, and p-value for our 8 secondary conditions, and the last 2 rows are male and female. But we need to add a column for male and female, and we need to change some column names, and then there are some columns here that are not really informative, so we can select which columns we want to include in our final table. So first, let's set that table that we just made. Let's call it chi-squared table. So we're just setting it to that object name. So now again, when we call chi-squared table, we get our table. This is good. Now we want to, on the chi-squared table, we want to add a column called health variable, which includes the names of all of our health variables. right? So these are the health variables, and then the sex variables, male and female. So let's create that column and attach it to the chi-squared table. And now when we call in chi-square table again, you see we have this last column on the end called health variable. So now we know what numbers are for what health variable. And from the chi-squared table, we want to select the columns in this order. We want health variable first, then we want the proportion column, which we will rename as pop_prop for population proportion, and you can rename it anything you want. The important thing is that your rename goes in quotes and it comes before an equal sign of the existing column name. So I've done that for a couple of the column names. So we have, first we want the population of the proportion, which is that column that's currently called proportion, then pop_SE, which is currently called proportion_SE, the disability proportion, which is currently called proportion 1, disability SE, which is currently called proportion_SE.1, the non-disability proportion, which is currently called proportion.2, the non-disability SE, which is currently called proportion_SE.2, and then fstat and p-value, we won't rename that, although you could if you want to, but to me that makes sense. So let's select our columns. Oh, that's the PowerPoint. All right, what I wanted was R. So let's select our columns. And now we have, this is our table. So we have our health variable, population proportion, population standard error, disability proportion, disability standard error, non-disability proportion, non-disability standard error, f-test statistic, and our p-value. So this is the table that they have in the article. Right, we recreated their table. Great. So that's all of the analysis. Now, in terms of our hypothesis that California girls would have better health than California boys, if I really wanted to test that out, what I would want to do is run survey chi-square, where our formula is tilde disability plus whatever health statistics. So let's do limit join 3 as an example, plus then I would want to look at the sex variable. And I would want to specify CG17_ chi-square_ design, our survey design. Is that right? Survey chi-squared. This is our formula having 3 variables. Okay. But the survey chi-squared function can only take 2 arguments in the formula right now. So if I really wanted to look at sex differences, I would have to create 2 separate data files and run the analysis that we did today twice, and then look at the tables side by side. And I don't want to do that. I feel like, you know, that would just be a lot of extra time, and we don't really need to worry about that right now. Which is why I created these 2 variables called male and female, just so that we could get an idea about the total disability rates across the population for male and female. So for male, 20.3% of people have a disability. For female, 23.9% of people, I should say 23.9% of females in California have a disability. These are the standard errors on this, and so those standard errors are actually quite small. So if you look between 20.3% for male and 23.9% for female, females have more disability than males. So when we're thinking about our overall statistic of overall hypothesis of California girls having better health than California boys, actually California boys win this one. So California boys have less disability overall than California girls. All right, so that's just an aside. Anyway, now you know how to do chi-square tests. Now you know how to format your data into a nice table to replicate what they showed in that article that we were working from today. Yep, that's all I have for this segment. All right, so I'm going to close out my R session. Don't want to save my workspace image. And yep, all right, well, thank you for joining me this time. During the next time, I think I'm going to be working with cleaning some continuous variables, so stay tuned for that. Great, thanks. Bye.